This is actually called the spectral theorem. We're trying to prove that an operator O, if we have a complete set of eigenstates and eigenvalues, can be written in this form. Now, we put O into the basis of eigenstates the same way we put it into any basis. We use the completeness relation. So we multiply by 1 at the start and 1 at the end. And then we expand out 1 in terms of our eigenstates. This is a complete orthonormal set of eigenstates, so all I need to do is take the sum of all the projectors, and that's 1. And I can do it on the other side as well, remembering to use a different dummy index. And then all I end up with is my O acting on this k is going to give me my eigenvalue, lambda k. It's a number, so it can come right out. And the inner product between j and k is a delta function. And so I can get rid of one of these sums, get rid of the k, and there we go, as desired. There's the spectral theorem. So just as the eigenvalues of the observable are the numbers that we measure when we make a measurement, the eigenstates of the observable are the state that we leave the system in. And we know that if we have a system that's initially a superposition of different values for some measurement, like different polarizations or different positions, then after the measurement, when we've got a particular measurement of polarization or a particular measurement of position, then we can trust that if we measure it again instantaneously, we'll get the same answer. So the state must jump to one of the eigenstates when we get a particular measurement of the eigenvalue. And from that, we can work out the measurement postulate. So everything may be described by an element of a Hilbert space, but to get the numbers out, we need the measurement postulate, which goes like this. So if a system is described by a ket psi, then we expand that ket in terms of the eigenstates of an observable O. Then whenever we measure the observable O, or the property associated with the observable O, then we get one of those eigenstates with probability times the modulus squared of those amplitudes, and the state immediately jumps to that eigenstate. The idea that quantum states would jump, that they'd have this probabilistic behavior, was very unsettling to physicists at the time when this theory was first introduced, and it's been very unsettling indeed to physicists throughout the last century. The reason for that is that probabilistic behavior suggests that there's things you don't know. It suggests that this is an unfinished theory. It was also really unsettling that things seem to act differently when you were watching them and when you didn't. Notice that measurement is what causes this, and it seems very odd to have measurement be a really important element of the description of how a system behaves dynamically. The history of the last 100 years of research on the topic, however, has showed us that basically any theory that gives the same answers as quantum mechanics has to share these very unsettling properties.